Today is Monday, right? Uh-oh. My cam freeze? It did. It did. Okay, we're back. Okay, I'll start recording. All right, so for today's live stream, I'm going to be going over the problems that we did today in class, and also there was a request for me to do a couple of problems, or a problem concerning if you have multiple charges, finding what the a condition for the electric field being zero at a particular point. So if you have any other requests for things for me to go over, just post in chat and I'll try to get to them as we go. Okay, so to start out with, let's first go over one of the questions on the old exams that was one of these questions where we wanted to find a condition for the electric field to be zero at some point. Okay, so we're told here that you have some circle of radius r, and this is a point at a comma 0, so it's a point on the x-axis, some distance a from the origin, and you also want to put some unknown charge here, q, so that if this has some distribution of charge we'll call lowercase q, we want to find what this q has to be so that the electric field here is zero. So in order for that to be true, what we can say is the sum of the electric fields produced by this point charge at the origin and the charge that's distributed over this arc is going to be equal to 0. And so if I call this some point 1 and I call the arc 2, what this says then is for the electric field to be 0 here, the sum of E vector 1 plus E vector 2 is equal to 0. Okay, so we can first start off by finding what E vector 1 is. This is pretty straightforward because it's a point charge. And so that's to say that in general for point charges, the electric field is going to be 1 over 4 pi epsilon naught q divided by r squared times r hat. And so the q that we have here is just going to be this capital Q. The distance from here to here, which is r by definition, is the distance a, and then r hat is going to be the unit vector that points from here to here, which is just going to be the positive x hat direction. So that's to say that E vector 1 is going to be equal to 1 over 4 pi epsilon naught capital Q divided by a squared times x hat. Okay. So the next thing that we need to do here is we need to figure out what the electric field is produced by this arc. Okay, and so in order to do that, what we say is dE is equal to 1 over 4 pi epsilon naught dq divided by r squared times r hat. And we just need to determine a couple of things here. So let's start with dq. dq in general is going to be equal to lambda dl. So if I have this charge q evenly spread over this arc of a half circle that has some total arc length of pi times r, and so that says then that lambda is going to be the total charge q divided by the total length, so this is pi times r. dl is going to be equal to r d theta because we're dealing with the arc of a circle. Now r, lowercase r, is going to just be capital R because the distance from any one of these dq's is just going to be the radius. So this is just going to be some capital R. Okay, so now the next thing that we need to do is we need to define r hat, and by association we need to define some theta here. So the way that I'm going to do this is I'm going to draw some imaginary line here, and then draw this, this arrow representing r hat. So it's pointing from dq to the point of observation. And then I'm going to define this angle theta here. So if I continue this down here, this is my angle theta. R hat then is going to have some part in x and some part in y. And then based on the angle that I defined here, we just need to figure out which trigonometric ratio is going to be which for the x and the y component. And so we see for the x, this is going to be the opposite, and this is going to be sine. So this is going to be sine of theta. And the thing that's important about this is that this r hat's going to be pointing in the positive x direction. And so that says that this is going to be a plus sign. And now this portion right here is going to be some cosine, but it's going to be negative because the y hat portion is going to be in the negative direction, so this is going to be a minus cosine of theta. Okay? The last thing we need to do to find what E vector 2 is to put all of this together. And so when we do that, we see that E vector 2 is going to be equal to 1 over 4 pi epsilon naught. I'm going to pull my lambda out front because it's just going to be a constant in this case. So this is q divided by pi. So that's going to make this a pi squared. This r is going to cancel with this r that I have for dl. So really I could just put this as a q here. Times the integral from 0 to pi, because the way that I've defined this angle here, theta is equal to 0 is going to be this, this portion here, and then I'm coming around to theta is equal to pi, times d theta times sine of theta x hat minus cosine of theta y hat. Okay? So something that I notice here based on the symmetry of the problem, the fact that this charge is evenly distributed, is that for every point down here there's a point up here, so that the y components of this electric field are going to cancel each other when I do this integral. And so I can actually just neglect doing that portion of the integral because I know by symmetry that it's going to be 0. So then what I need to do is I need to integrate cosine, or sorry, I need to integrate sine, which is going to give me a minus cosine. So the next line that we have here is this is 1 over 4 pi squared epsilon naught times q times a minus cosine of theta evaluated from 0 to pi. And so when I evaluate this, this is going to give me a minus -1 minus 1. And so that tells me that ultimately I'm going to get a factor of 2 from this. I lost an r squared. There's an r squared here in the denominator because of this. So there's also this factor of r squared here. So when I do that, ultimately what I end up seeing is that this is going to be equal to, and I have an x hat here as well because of this. This is going to be equal to q divided by 2 pi squared epsilon naught r squared in the x hat direction. So this is what my E2 is. Okay. So putting this together with the equation that I wrote up here, the condition for the electric field being 0, I can put this together in one equation. And that's going to say then that this is my E1, this is my E2, and so 1 over 4 pi epsilon naught q divided by a squared plus q divided by 2 pi squared epsilon naught r squared times x hat is equal to 0. And now I'm just working in one dimension, so I don't really need to worry about the x hat carrying this through. But what we see is we can solve for capital Q. So the first thing I can do is I can cancel my epsilon naughts. Those are going to be common to this. And then I'm going to move this to the other side. And so I have Q divided by 4 pi a squared is equal to minus q divided by 2 pi squared r squared, and then move some things around to find our answer. And so when I do that, what I end up finding is that q is going to be equal to negative 2q divided by pi times a squared divided by r squared. And that's our answer. Okay. Now, let's see if this answer checks out, because we can have some intuition about whether this q should be positive or negative, and then something about the dimensions here. So if this q is positive, that's going to cause electric field going this way. If this q is positive, it's going to give me electric field in the same direction. But what I want is I want electric field at this point that's going to be 0. And so if this one's going to be positive, making electric field go this way, this one needs to be negative to make electric field go that way. So that's why we have this negative sign. The second check that I can do is to see if this works out dimensionally. So this q has to have a unit of charge. Let's see if the right side has a unit of charge. So we have a unit of charge for this q. We have an a squared divided by r squared, so that's a meter squared per meter squared. So that's this term is dimensionless, and so we're only left with the q. Pi is just a constant. And so we know then that dimensionally this checks out. Okay. So the big takeaway from this problem, and any problem like it, you can ask problems if you want to find what some charge needs to be for a force to be 0 or for some electric potential to be 0. It comes down to the superposition principle, and you say that the electric field, the force, the electric potential at some point is going to be equal to the sum of all electric fields acting at that point. And then if it's going to be equal to 0, then you say that that sum is identically equal to 0. And so in this case, what that meant was we could find what the electric field was produced by this arc of charge. We could find the electric field produced by this point charge at the origin. And then when we add those two together, it's going to just be equal to 0. Okay. So I'll pause for a second and get some grapefruit juice. But let me know if you have any questions about what I did here. Okay. Okay, so based on the fact I don't see any questions, I think we're good to move on. So now what I'm going to do is I'm going to go through the classwork that we had today. Okay, so the first problem that I gave you was one of these problems where we give you some box or some cube, and we want to find what the charge is inside the cube based on the electric field that we also give you. And so what that boils down to is applying Gauss's law and finding what the flux is through all of the surfaces of the cube, and then saying that the flux that goes out of that cube is going to be equal to q divided by epsilon naught. And so that's to say Gauss's law just says that the integral over some closed surface of E dot ds is going to be equal to q in divided by epsilon naught. Okay. So for this problem, what I gave you was this is just a right-handed coordinate system in 3 dimensions. But I give you some cube that I'm going to do my best to draw here. This is okay. So there's our cube, and we know that these have sides of A, and it's offset from the origin, so that this is some point A, comma 0, comma 0, and this is some point 2a, comma 0, comma 0. Okay? And then looking at where you started, e2, what is that in front of the integral? Never mind. Look back at what I said, and if you can ask me a more specific question. It's kind of hard because I erased it now, but if you have a more specific question about it, then I can go back to it. Okay. So for this one, I tell you that I have some electric field in all of space given by E vector is equal to E0 x squared xy over a squared in the positive in the x hat direction plus some E0, I think this one was z squared over a squared in the z hat direction. Let me just check that to be sure. Yeah, okay. So we want to find what the charge is inside of this cube. And what that's going to mean is we need to find what the flux is through all of these surfaces. So in principle, there would be 6 fluxes that we need to calculate, but we're actually kind of lucky here because we see that this is just x hat and z hat. There's no y component. And so if we look at 2 of the surfaces, this surface, the right surface, and the left surface, this is going to have some unit vector that points in the positive y direction. This one has a unit vector that points in the negative y direction. And because of that, there's not going to be any flux out of either one of the 2 of these surfaces because our electric field doesn't have any component in the y direction. So we're down to 4 integrals instead of 6. So let's first start by looking at the top face. So for the top face, we can write down what our dA is by saying that dA vector is going to be equal to z hat times dx dy. And let's see why this is the case. Well, the unit vector that points perpendicular to the surface out of the box is just going to be in the z direction. Our infinitesimal pieces here, if I turn this and I look straight down at it, they're going to be in x and y, and so that's why this is z hat dx dy. Okay, so let's do this calculation for the flux out of the top. So when I do this calculation, I'm going to say that the flux is going to be equal to E dot dA, which is going to be equal to this whole thing dotted with this. But we see when we take this dot product, x hat dot z hat is going to be equal to 0. Oop. Yep. Yeah, I see it. I see it. Computers, how do they work? Properties. Yeah, let's just turn this on and turn it off. Okay, yep, we're back. All right, sorry about that. Last week it was the camera wanting to turn itself off. Now it's it just freezes, but I'll try to fix that as we go. Okay, so we wanted to find what the flux was out of this top surface, and so that's just to say that we have the integral of E dot dA for the top surface. We wrote down what dA was for the top surface, and then we need to take this dot product. Now I'm not going to write the whole thing because when I look at this, I'm going to have some x hat dot z hat that's going to be 0 because x hat and z hat are perpendicular to each other. And then when I do z hat dot z hat here, I'm going to get 1. So the term that we need here is just going to be this E0 z squared over a squared times dx dy. And because I have 2 infinitesimals here, this is going to be a double integral. Okay. So now let's look at this this integrand that we have here, and see we're integrating over x and y, but we have some z here. So that means we need to evaluate what this z is, and the way that we're going to do that is look at where the surface is. So for this surface, every point along it is going to have the same value for z, and that value is just going to be a, right? Because this is elevated from the xy plane some distance a. And so we can plug in a for z, and then this is going to reduce nicely, and so we're just going to have E0 times the integral of double integral dx dy. So you'll see I didn't put my limits of integration in here. That's the next thing we need to do. And when we do that, we want to ask ourselves, where does x start and where does y start and where do they end? Okay, so let's first start with y. So if I look at my picture here, y is going to start from y is equal to 0, right? And then it's going to move out to y is equal to a. So this is going to be y is equal to 0 to y is equal to a. And we'll do the same thing with x. X begins at a and it goes to 2a. So this is from x is equal to a to x is equal to 2a. Okay. So now when we evaluate this this integral, what we're going to get for x is just going to be x evaluated from a to 2a. So it's going to be 2a minus a, and so that's going to give me an a here. And then the integral of y evaluated from the integral of dy evaluated from 0 to a is going to give me another a, so this is going to be a squared. And so our flux out of the top is just going to be E0 a squared. And so this is phi top. Okay. Now let's quickly look at what the flux out of the bottom is going to be. It's going to look very similar to this. Our dA is just going to be minus z hat dx dy. And so we could do this dot product. I'm not going to write the whole thing here because there's something interesting that happens. When we're evaluating this electric field at z is equal to 0, we see that the electric field is itself 0. And so that says that phi for the bottom, we'll write this over here, phi bottom is equal to 0. Okay. Now let's look at the other two faces that we need to consider, the back and the front. And so let's first start with the back. So for the back, dA vector is going to be equal to, this is going to be equal to minus x hat dy dz. Okay. Again, we can see it's minus x hat because the back face, the vector that points perpendicular to it, is going to be in the minus x direction, and it's dy dz because that's where this the surface is spanned over. Okay. So when we do this flux calculation here, this is going to say again, integral E dot dA is going to be equal to, you get a negative sign out front for the dot product here and here because I have a negative sign. And then this is going to be E0 xy over a squared times dy dz. And so this is again for the back face. Now when we're looking at this one, we see something again similar to this case. We're integrating over y and z, but we have some x here. And so we need to evaluate where in x this this face of the cube is going to be. And when we do that, we see that for the back face, this is going to be at x is equal to a. Okay, so we can plug that in and then move some things on the outside. I have a over a squared, and we can bring that out all out front. So this is minus E0 divided by a times the integral of dy times the integral of y dy times the integral of dz. Okay. So now, again, we want to figure out where does y start, where does it end, where does z start, where does z end. Y, again, is going to start at 0 and go up to a. Z is going to start at 0 and go up to a. So this is from 0 to a, and this is from 0 to a. When we evaluate these integrals, the integral in y is going to give me a y squared divided by 2, and then we can plug it in a. And so this is minus E0 over a squared over 2. The integral for z is just going to give me an a. And so that's going to cancel this and this. And so that says, let me put some boxes around some of the important information here. So for the back, and I'm running out of space to write here. So phi for the back is just going to be equal to minus E0 a squared over 2. Okay? Now, the last one we need to do here is the front face. And so when we do the front face, we see that dA, so for the front, dA is going to be equal to x hat times dy dz. When we do the integral of E dot dA, I'm going to move this up right here, we end up seeing that this is going to be the integral of E0 xy divided by a squared dy dz. Okay? And again, we need to evaluate what x is for this front face. And so when we do that, we see that for all of the points on this surface, the value of x is going to be 2a. And so we can plug that in and then bring this all out front. And so this is going to be 2 E0 divided by a, integral y dy, integral dz. And again, just like this one, our y goes from 0 to a, our z goes from 0 to a, 0 to a, 0 to a. And then we can evaluate this. And so this is going to be 2 E0 divided by a times a squared over 2 times a. And so ultimately, that says that this is going to be E0 a squared. Okay. So now we have our three fluxes. We have the back, we have the top, and we have the bottom, or sorry, the front. And so when we add all of those together, what we end up seeing is this is going to be 2 E0 a squared minus E0 a squared divided by 2. This ends up being 4 halves. 4 halves minus a half is going to be 3 halves. And so this is going to be 3 halves E0 a squared, which is equal to Q in divided by epsilon naught. And then we can just rearrange to find what Q in is. And so Q in is going to be 3 halves E0, or epsilon 0 E0 a squared. Okay? And then that's pretty much it. So as a process, these problems really aren't that tricky. It's just a matter of what is the electric field that I give you, what are the dA vectors for the various surfaces that we have, and then evaluating what the flux is out of each one of these. And this turned out to be a little bit of a mess because I'm not used to working on a smaller board, but we're going to be doing a lot more of these tomorrow in recitation, so you'll get a lot more practice on them before the exam. Okay. So again, I'll pause here to see if anybody has any questions. Oh geez, we've already been going for half an hour, huh? Okay. All right, so it doesn't look like there are any questions, so I'll move on to the next one. So for the next one, this one is kind of the first problem that we'll have where we have some spherical symmetry. And so in this problem, I give you some electric field that points in the radial direction, and it's inside, we want to find what the charge is inside of some circle that has some, or some sphere rather, that has some radius of a. Okay, so let's go ahead and draw what this looks like to start with. And so here's the coordinate axis I have. This is x, y, and z. And then there's some sphere of radius a. And I tell you that the electric field E vector is going to be equal to, I think it was E0 r to the 4th. Yeah. This is going to be E0 r to the 4th divided by a to the 4th times r hat. Okay. And again, what we want to do is we want to find what the charge is on the inside of this sphere. And so in order to do that, we're going to apply Gauss's law. So that says the integral over the closed surface of E dot ds is going to be equal to Q in divided by epsilon naught. And now we're going to play some games with this E vector and this ds. And we'll see that something really interesting happens here. So if we have this sphere, we know that the unit vector that points normal to the surface is going to be this r hat. Okay? So when I'm not going to plug the whole thing in here, I'm just going to say this is going to be equal to E as a function of r times r hat. So when I plug this in here, this is going to be E as a function of r times r hat, dotted with ds vector. Ds vector can be written as r hat ds, right? This is just the magnitude and direction of this. And so when I do that, this is going to be r hat dot r hat times ds. And so this simplifies nicely because this r hat is in the same direction as this r hat. And so this is going to be E as a function of r times ds. Okay, so let's pause here and talk about this. Now you might not think it's so remarkable that I came from here and I got to here. What's the difference really? But there is a big difference, and it's the fact that I have vectors here that are multiplied via a dot product, and now these aren't vectors anymore. They're just going to be magnitudes. And so the thing that's really useful about that is if I look at what the flux is out of any one of these ds vectors, for every one of them on the surface, it has the same r hat behavior. And so getting rid of that cosine of theta that we might have had here actually is a big deal for this calculation. So the next thing that I can do is I can say, well, if I evaluate the electric field on this sphere, it's always going to have the same value. It's going to be the same value in terms of its magnitude here and here and here, which means that E at the point A is just going to be a constant with respect to the variables of integration. So the next simplification I can make here is I can say that this is E at A times the integral of ds. Okay. Now this is also a big deal to get to this point, because now I don't have any argument for my integral, and so what I can do is I can say that this is just going to be E times E evaluated at A times S, just the surface area of this sphere. And we know that surface area of the sphere is just going to be 4 pi r squared, and this has some radius of A. So now let's go ahead and plug everything in here. This says that this is going to be E0 r evaluated at A is going to give me an A to the 4th over A, and so this is just E0 times the surface area, and so this is 4 pi A squared. So that takes care of my left-hand side of Gauss's law. For my right-hand side of Gauss's law, I'm just going to have Qn divided by epsilon naught. So this is Qn divided by epsilon naught, and I can solve for Qn. So in the end, I see Qn is going to be equal to 4 pi A squared epsilon naught E0. Okay? And so something that we see with this problem compared to the last problem is when we're dealing with spherical symmetry, a lot of times the calculations end up being a lot cleaner, a lot easier than when we have to deal with cubes. And that's actually, it's no accident that that's true. And it's ultimately, after the exam, we're going to start talking more about the symmetries that you can apply with Gauss's law and how you can get very nice answers to come out of it, as opposed to trying to apply Coulomb's law to do those calculations. You could do them either way, but the Gauss's law calculations end up being like 2 or 3 lines. The Coulomb's law calculations, if you're unlucky with what it is, it could be something that's 2 or 3 pages. So that's this one. So I'll pause here and let you guys ask any questions if you have them. I have one more question from the work that we had in class today after this, and then I'll open it up for any questions that you guys have. I don't really have anything else planned anyway. Okay, so it doesn't look like we have any questions, so I'll move on to the next part. And that is to find the difference in electric potential between a point A and a point 2A for this electric field. So I'm just going to erase the Gauss's law portion that I have here and just leave what I have up there. And so in order to do this part, what we're going to do is we're going to say that the electric potential V is just going to be equal to the negative integral of E0, or in general, it's E vector dot dl. Okay. So because we're working in spherical coordinates or polar coordinates in this case, dl can be written as, well, in general, I should do it in spherical coordinates, but I'm going to be lazy and do it just in planar polar coordinates because it doesn't really matter. This is just going to be equal to r hat dr plus theta hat times r d theta. Okay. So when I take this dot product, I see that this only has a component in the r hat direction. So this portion's 0. And like I said, in general, there should also be a phi component here, but that portion will also be 0. So when I do this dot product, what I end up seeing is that V is going to be equal to the negative integral of E0 r to the fourth over a to the fourth times dr. Okay, and this is an integral that we're able to do pretty easily. This is just some power, and so this ends up giving me, this is equal to minus E0 divided by a to the fourth times r to the fifth divided by 5. Okay, so this is what my electric potential function looks like. But what I ask you here is to find the difference in electric potential between some distance a and some distance 2a. And so in order to do that, what we say is that V at 2a is minus V at a is going to be equal to, this is minus E0 divided by 5 a to the fourth times, this is going to be 2a to the fifth, 2a to the fifth, minus a negative E0 divided by 5a to the fourth times a to the fifth. Okay, I just evaluated this function at these points here. Okay, and so 2 to the fourth, 2 to the fifth, 2 cubed is 8, 2 to the fourth is 16, 2 to the fifth is 32, and so this is minus 32 E0 divided by 5, a to the fourth, plus E0 divided by 5, a to the fourth times a to the fifth. And I also have an a to the fifth here. And then I want to take some magnitude of this in the end. So this ends up being minus 31, but I want an absolute value, and so this is going to be 31. I can cancel a power of 4 powers of a in the denominator, so this is 31 over 5 E0 times a. So this is the magnitude of delta V is equal to this. Okay. Why are you not making the same argument as you did in part 1 in respect to the r to the fourth and a to the fourth? Okay. So yeah, this is important. That's a good question. This comes down to, and we've seen almost all of these kinds of vector integrals that we're going to have, but we're going to add to it when we do magnetic fields later. But this really comes down to the difference between what do these two equations mean. So I have this integral of E dot ds, and I have this integral of E dot dl. And so there's some interesting things going on here, and there is a really big difference between what these two mean. So integral E dot ds, I'm calculating a flux. So this is to say that I want to find what the electric field is going out of the surface at by summing what it is at each point times the area, okay? And the reason why I evaluated my electric field in this one and I didn't evaluate the electric field in this one is because it has all the same value over the surface. I'm adding up all of the electric field over the surface as opposed to the E dot dl, which is telling me really I want to find what the sum of all contributions of the electric field are along some path. And so because I'm going along some path, at every point along this path, the electric field has a different value. So it's really, oh, I froze again. Let me fix that. Yeah. This technology never cooperates with you the way you would hope it would. Okay, yeah, I'm back. That's the real point, and it's a good question because on a surface level, these two equations look very similar, right? Barring the circle here and barring the S versus L, I have some E dotted with something, but the meaning of them is very different. And so let me illustrate even more what I mean when I say the meaning of these is different. This ds is itself two infinitesimals, and what it's doing is I'm taking, let me kind of zoom in on this surface here. I have some ds and I have some E. I'm taking all of the components of E that are in the same direction as ds and I'm adding them up over the entire surface. And that electric field on this surface always has the same value. But when I'm doing this integral E dot dl, what I'm doing is I'm saying, here's some point at the origin. That's the circle that I had before, so this is at some point r is equal to a. R is equal to capital A. And this is some point r is equal to 2a. I have some path that I'm following. So it really comes down to the difference between what does ds mean and what does dl mean. ds is some surface element that has some vector that points away from the surface. dl is some infinitesimal line element that points in the direction of the path that I'm moving in. And so that's why I evaluated what E was here, because it had the same value over the entire surface. Whereas I have to integrate over the function E as a function of R, because at every point along this path it has a different value. And that's really the reason why I'm doing that. So digest that a little bit and see if that makes sense. And if you have another follow-up question, let me know. So opening this up for other questions, are there any problems on the previous exams or problems that we did in class that I didn't have time to go over that you have questions about? I'll solve those now. If you don't have one, I only have 15 minutes. I can find something. But I don't want to do the problems that you'll do tomorrow. Nope, don't want to go to Rate My Prof. Want to go to Tatiana's website. Then previous tests. Let's just take a stroll down memory lane and let's just solve the test that I took. I won't tell you what year this test is from, but if you look at it later, you'll be like, ah, well, Dr. Wu is old. I know what year he took this class. That's test 2. It's test 1. Okay. So it's because it's now a part of the function we leave the a in, and at the endpoints is the only thing. Yeah. So when I wanted to find delta V, this was defined to be V evaluated at 2A minus V evaluated at A. And so the first thing that I did was I had to calculate what the electric potential function was from V is equal to minus integral E dot dl. So once I had that function, I was able to say, well, the electric potential at 2A is just the function evaluated at 2A. The electric potential at A is the electric potential function evaluated at A, and then I just take the difference of the two in order to determine this final answer that I erased now. Okay. And the endpoints are the only thing. So now this function, now because it's part of a function, we leave A in. Well, to answer your question a little bit more directly, evaluating this 2A and this A, that's the last thing that you do. You have to calculate what, you just go through the process of saying, I know what E is, I can figure out what dl is, do the integral to find the electric potential function, and then evaluate it at the endpoints. That's the thing that we did. Okay, so going to exam, and this is, I'll tell you what year I took this so you can follow along. This is 2006, so this is the oldest exams that they have on there. That was the year that I took this class. So the first question is one that has some distribution of charge. And what is it that we're trying to find? Is it the electric field? Find the electric field. I'm going to have to be more creative with the problems that I come up with, because this was actually a question that I had thought of for our exam, but I don't want to ask something that you've explicitly seen. So this goes from, this is y is equal to A to y is equal to B, and then this is some point C along the x-axis. And so this is some charge that's of Q that's uniformly spread. This Q is uniformly spread. So as always, when we have one of these kinds of problems, we want to find what the electric field is. And so we first start by writing down the equation for the infinitesimal electric field. So that's to say that dE vector is equal to 1 over 4 pi epsilon naught times dq over r squared times r hat. So let's first figure out what dq is. In general, dq is equal to lambda dl. And so lambda is going to be equal to the charge per length. The total charge, so lambda is equal to the total charge q divided over the length that it's spread over. So this is going to be a length of b minus a. So this is b minus a. dl is just going to be dy, because that's where our infinitesimals reside, in dy. Now, to find r, what we want to do is first draw in what r is. So this is what r is. It's the distance from each one of these dq's to this c. So we know that this side is going to be some side c. This side is going to have some arbitrary values that are going to change for each one of these. And so the way that we'll denote this is to say that this is going to be some y. Okay. So what we can do then is we can say that r is going to be equal to the square root of c squared plus y squared. Okay. Last thing we need to do is figure out what r hat is. So I'm going to draw some theta in here. So r hat is going to be some part in x plus some part in y. Looking at the angle theta I have defined here, this is the adjacent side. So this is going to be some cosine of theta. And then for the y portion, this is the opposite side, and so this is going to be some sine of theta. And more specifically, this is going to be a minus sine of theta, because this is pointing down in y. So this is minus sine of theta. Okay. Now, because our variable of integration is y, we need to parameterize this cosine and sine of theta in terms, oh, it froze again. It froze a long time ago too. Okay, so where is this? Properties. Turn this off. Turn this on. Okay. So I'll let you guys digest what I've written here now. So what I've done since it froze, I'm trying to find what r hat is, and so I labeled this angle of theta and this angle of theta, so that I can figure out this is r hat as labeled in the diagram. It's going to point down in this direction, and then what I said was the x portion is going to be some cosine because that's the adjacent side to this angle, and the y portion is going to be sine because it's the opposite. But it's also going to be a minus sign because this is going to be in the negative y direction. Okay. So the next thing that we need to do, because we're integrating with respect to y and we introduce this theta here, we need to write cosine and sine of theta in terms of y. Okay. So in order to do that, we can say that cosine, looking at this triangle, is going to be c divided by r. So this is going to be c divided by r times x hat, minus sine is going to be y divided by r. So this is minus y divided by r times y hat. Okay, so now all we need to do is put all of this together. And so that's to say that E vector is going to be equal to 1 over 4 pi epsilon naught times lambda, which is going to be Q divided by B minus A. I'm pulling it outside the integral just because it's a constant, times the integral. We have an r squared here, and we have an r in the denominator for both of these, and so that's going to make an r cubed. And r is the square root of c squared plus y squared, and so that means that this is going to be dy divided by c squared plus y squared to the 3/2 times the remaining piece of our unit vector, and so this is going to be c x hat minus y hat. Okay. Now we need to, the last thing we need to do here is put in our limits of integration, and that's to say that this charge starts at y is equal to a and goes to y is equal to b. So this is from a to b. Okay. And if this was a question on an exam, this is where we'd stop. I wouldn't ask you to do an integral like this. You'd have to do a u sub for the y component, and then you'd say here that y is equal to c tangent of theta for the x component. You can do trigonometric substitution to do that, but this is where we'd stop. That would be the full answer. And so just to give you some idea of how I would grade this, if these would be like 25-point problems, I would say probably 5 points for writing down this. How many do I have left? I have 20 points. Maybe 3 or 4 for this, 3 or 4 for this, and then 3 or 4 for this, 3 or 4 for this, 3 or 4 for this, and then like 1 or 2 for putting it together in the answer. So the majority of the points are going to come from identifying what all the pieces are in order to do this. And then there's also some points for the limits of integration. That might be 2 or 3 points. Okay. Any questions about this one? We'll move on to the next one if there's no questions. Okay. Hopefully it's not frozen. It's not. Okay. On to the next one. And so I'll do another live stream on Wednesday night. So like last minute panic mode. How do I solve this problem? And I'll let you guys ask me questions on those previous exams, and I'll try to answer them. So how are we doing on time? So this will be the last one that I'm going to do. So for this problem, what we have is some charge of Q1 that's going to be at a point Y1 on the y-axis, some charge Q2 that's at some point y2 and x2, and some charge q3 that is at some point y3 and x3. And does it give us what these are relative to each other? This is a minus q3. Okay. And what we want to do is we want to find the force on Q1. Okay. Need better chalk. Okay. So in order to find the force on Q1, what we need to do is we need to find the force that Q2 acts on Q1 and the force that Q3 acts on Q1. So F3 acting on 1. Okay. So let's break these apart, and I'll do the F2 one here, and I'll do the F3 one up here. Okay. So this is just going to be 1 over 4 pi epsilon naught Q1 Q2 divided by r squared times the unit vector that points from Q2 to Q1. So this is going to be r hat 2, 1. So r hat 2, 1. Okay. So the first thing that we can do is we can figure out what this distance is. This distance here we can determine by adding another little piece to this triangle here. And so this r is going to have some component of x2 in the x direction, and so this is going to be x2 squared. For this portion right here, this is a total distance of y2, this is distance of y1, and so this is going to be y2 minus y1. So this is plus y2 minus y1 squared. Okay. Now the next thing that we need to do is to figure out what this unit vector here is, r21. So r hat 21. This is going to have some part in x and some part in y. Okay. So if this is some angle of theta here, in x this is going to have some cosine of theta, y is going to have some sine of theta, and they're both going to be negative. So this is going to be minus cosine of theta minus sine of theta. And then based on the triangle that I have here, this is going to be minus x2 divided by r x hat minus y2 minus y1 divided by r y hat. Okay. So now we have all the pieces that we need for this. We really only need to determine what r was and what r hat 21 was, and then we could plug everything in here. I'm not going to go through that process. I think you guys understand what we need to do there. But I will go ahead and calculate what F31 is. So for F31, this is going to be 1 over 4 pi epsilon naught Q3 Q1, where Q3 is actually negative, right, because it's minus Q3, divided by r squared times r hat 31. Okay. So again, we just need to figure out what this distance is here. So this is now my r. Let's call this r sub 31. And what this unit vector is. So now that I've done the two part, I'm just going to erase that to clean this up a little bit. So this is my r hat 31. This is some y1 where q1 is. So q1 is at this point y1 along the x-axis or the y-axis. And then what we want to do is we want to first figure out what r31 is. So r31 is going to be equal to this whole distance in x squared, so under a square root, this x3 squared. And then the distance in y that we're looking for is this distance. And so if this total distance is y1, this is a distance y3. This is going to be y1 minus y3. So plus y1 minus y3 squared. And now the last thing we need to do is figure out what the unit vector is. So we can put some angle theta here. That's going to be the same angle theta that I have here. So r hat is going to be equal to r hat 3, 1 is going to be some part in x hat plus some part in y hat. Make sure we're not frozen, we're good. So this is going to have some minus cosine of theta in the x hat and some plus sine of theta in y hat. Plus sine of theta in y hat, okay? So again, just like we did before, we just need to figure out what cosine and sine are in terms of the sides of the triangle. So when we look at the cosine of theta, this is going to be, let's call this a 2, 1, 2, 1, just to distinguish this. This is going to be minus x3 divided by r 3, 1 x hat plus the opposite side is going to be this y1 minus y3. And so this is going to be plus y1 minus y3 divided by r 3, 1 y hat. Okay. And then again, the last step is just going to be plugging all of these in to find what f vector 2, 1 is, what f vector 3, 1 is, and then say that f total is going to be equal to f 2, 1 plus f 3, 1. And then that's it. Okay? So I'll pause for a second and answer any last questions if you guys have, and then that's going to be it. But like I said, I'll do another live stream on Wednesday night as well, if you guys have any last minute questions. Hopefully the camera doesn't freeze. Okay, well, if that's it, then that's it. I'll see you guys in recitation tomorrow. Be working on those practice exams. I postponed the homework until next Wednesday. So the homework that I gave today isn't going to be due until next Wednesday, to give you guys some more time to go through those practice exams for the test. Otherwise, I'll see you guys tomorrow, and have good luck studying.